Okay, good morning, my calculus people. This is day 2 of differential equations. This is what it's going to look like for the most part. Okay, remember we're using separation of variables to get the y things on one side and the x things on the other, including dx and dy. And then we use our initial condition to solve for that constant of integration. And once we solve for c, then we go back in and we solve for y. Okay, this is the one that's going to be the most difficult. This one is algebra intensive, like all the algebra you've ever learned since the 8th grade is going to be involved. But with practice, we will be able to remember the algebra, and the steps are repeated over and over and over and over. Okay, so once you do a couple, hopefully you'll have all of them. So let's look at this first example. dy dx equals 6x squared times y. Okay, so we're going to, once again, multiply both sides by dx. So we have times dx over here, and we're going to divide both sides by y. So our equation looks like dy over y equals 6x squared dx. Okay, so first we separate our variables, get y and dy on the left, and get x's and dx on the right. Now, it's great if you recognize, right? The math, sorry. We have to do the calculus, which is to take the integral of both sides, right? We are integrating both sides in order to solve this differential equation to see what these equations were before we took their derivatives. Now, this part, the left side, it's really important to understand what the antiderivative of 1 over y is. Okay, because this is going to happen a lot. We're going to get 1 over some type of a linear equation. Okay? And when we take the integral of 1 over some type of a linear equation, that becomes the natural log antiderivative. Okay? So if we have 1 over a linear, now depending on what the linear is, it might have a coefficient. We might have some type of a fraction out here. Okay? 1 over a. So as if our linear equation was ax plus b, right? That was our linear equation. Then we're going to have 1 over a as our, right? In order to stem the chain rule effect of taking the antiderivative of a linear. Okay? But really important to understand, 1 over a linear equation is going to be 1 over a, right? A is your coefficient of x, times the natural log. These are natural log antiderivatives. And whenever we take a natural log antiderivative, we need to have these absolute value bars. Okay, it's important to have absolute value because we can't take the log of a negative. Okay, that's not part of the domain for natural log. So that's going to happen almost every single time today at least, but lots of times on these type of equations. So dy over y, that is the antiderivative of natural log y. And the antiderivative of 6x squared, 6x to the 3rd power divided by 3. Okay, we add 1 to the power, and then we divide by our new power. 6 divided by 3 is going to be 2. So we can just rewrite this, and if you need to take another line, that's okay. This is 2x cubed. So now let's plug in our initial condition. We have an x value of 0, and we have a y value of -5. So -5 is an absolute value. 2 times 0 cubed plus c. Well, 0 cubed, hopefully you know 0 cubed is just 0. So the natural log of the absolute value is natural log of 5. And you can leave that in parentheses if you want to. natural log of 5, or you can take it out of parentheses. It doesn't really matter. Mathematically, it means the same thing. Okay, done. We have solved for C. So now we're going to plug this back into our general form so that we can find the particular solution. Natural log of y equals 2x cubed plus the natural log of 5. Now we have to solve this equation for y. Okay, and here's some pretty tough algebra. So number one, how do we get rid of a natural log? That's the question, right? How do we solve any natural log equation? We do it by exponentiating. In other words, we make both sides into exponents. And if they're going to be exponents, that means we need a base. So what is the base going to be in order to get rid of our natural log? Right, we want to get rid of natural log. So what base gets rid of natural log? That's the question. And the answer is base E. Base E. So we're going to take both of these and we're going to raise them to a power, right? They're going to become powers, and the base is going to be E. So we have E raised to the natural log of y power equals E raised to the 2x cubed plus natural log of 5. This whole entire thing is a power. Okay, and this is a power also. Well, we do this because what is E raised to the natural log? Right? These are inverse operations. E raised to a natural log, in essence, cancels each other out. And we just get y. Y equals E to the 2x cubed plus natural log of 5 power. Right? All of that is in the power. Now, we're going to do some simplifying. So I'm going to remind you of a little rule from Algebra 2 about exponents. Okay, so let me come over here and write that down, your rule about exponents. If I had x to the third, that's not a very nice looking 3. If I've had x to the third times x to the 7th, how can I simplify those exponents? We simplify them by adding them together. Okay? If I am multiplying with the same bases, I add exponents. Okay? Now, I'm going to go in the opposite direction. I currently have a plus in my exponent. So what I'm going to do is I'm going to take the plus and raise each one to that separate base. So x to the 3 plus 7 is x to the third power times x to the 7th power. Okay, that's one of our properties of exponents. So if I apply that here, right, notice that I have a sum in my exponent. So I can make e to this power times e to the natural log of 5 power. Okay, this is how we're going to simplify. E to the 2x cubed power times e to the natural log of 5 power. Okay, so I'm using that property of exponents that says if I have an addition in my power, or in my exponent, I can change that into multiplication of multiple bases. Right, so if I had 3 things added together in here, I would have 3 bases multiplied together. Okay? So that allows me to do this. What is e raised to the natural log power? Right? What happened to e to the natural log over here? They cancel out. Okay? They also cancel out here. So if I have e to the natural log, they cancel out. What's my number that's left? 5 is my number that's left. And we put the number in front of our exponent. So 5 times e to the 2x cubed, and that is our answer. Let's look at another example of the similar style. Y prime equals y plus 3 over x squared, right, where x doesn't equal 0. Right, that's a caveat, because if x equals 0, then this is undefined. It would have a vertical asymptote there. So as long as x is not equal to 0, this is how we are defining our derivative. And this is our initial condition. This helps us calculate c. Okay, so separation of variables. Y prime is dy dx. Y plus 3 is in our numerator, and x squared is in our denominator. Okay. How do we move our dx from the left to the right? Multiply. And what do we want to move from the right to the left? Y plus 3. How do we move something that's in a numerator? We divide. We divide by y plus 3. So we have the equation dy over y plus 3 equals dx over x squared. Remember, dx or x squared is in the denominator here, so it needs to stay in a denominator. So we have dx in the numerator over x squared in the denominator. Okay, so that's the first part, is doing the algebra in order to separate our variables. And now comes the calculus. Take the integral of both sides. Okay, we recognize, hopefully, this left side, right? We have dy over a linear. This is going to give us a natural log antiderivative. Natural log of y plus 3. So notice the coefficient of y is 1, which is why we don't have a 1 over 1 here. Okay, but if this were a 2y plus 3, then we would have a 1/2 in front. Okay, equals. All right, let me come back up here. I'm going to rewrite 1 over x squared, right? X squared is in the denominator, so I'm going to rewrite it as a negative power. Okay, because I want to apply the power rule, and I can only do that when we have a numerator, right? We don't do it with denominators. So 1 over x squared can be written as x to the negative 2 power. So our rule says add 1 to our power and multiply by, or rather divide by your new power. So dividing by negative 1. Okay, just to stay consistent with our rules, we add 1 to the power and we divide by the new power. Okay, so doing a little bit of simplifying, we can put this back in the denominator. So natural log of y plus 3 equals negative 1 over x plus c. Okay, that's the best way to write this antiderivative. Let's solve for c. So I have an x value of 2 and a y value of 1. X of 2 and a y of 1. So 1 plus 3, that's positive 4. Okay, so we don't need to have an absolute value around a positive number anymore. You can leave it in parentheses if you want, or we can take the parentheses away and just write it as natural log 4. And then I'm going to add 1/2 to that side. So my c value is the natural log of 4 plus 1/2. So let's take that and we'll move it back up into, I guess, here. That was where my equation was. I can do it down here. So I have natural log y plus 3 equals negative 1 over x plus natural log of 4 plus 1/2. Okay, how do we get rid of natural log? Right, we exponentiate it. We make both of these things into powers. with a base of e. Okay, now we simplify. E and natural log cancel each other out, right? They are inverse operations. So I get y plus 3 equals here, because I have plus, I'm going to change this to a bunch of e raised to the powers. Okay, just like we did before. That's e to the negative 1 over x times e to the natural log 4 times e to the 1/2. Okay? Right, that's using that property that we had in our last one, just kind of exponentiated here. So this becomes e to the negative 1 over x. E to the natural log of 4 is 4. And then I have e to the 1/2. So if I'm raising something to the 1/2 power, that's also known as what algebraic property? The square root. Okay? You could also leave it as e to the 1/2. Right? Remember, e is a constant. So e to the 1/2 square root of e is a number. So we could technically put it in front here. 4 is a number. Square root of e is a number. I don't know. You can see it lots of different places. But our last step is to subtract the 3. So we'll put the minus 3 after all that. And this is our equation in all of its algebraic wonderfulness. Okay, let's look at a word problem. Okay? The rate at which a puppy gains weight, right? This is your dy dx. When you see the word rate, you need to think derivative, you need to think slope, you need to think dy dx. Puppy gains weight is proportional to the difference between its adult weight and its current weight. So it gives you a nice equation right here. You don't have to make your own equation. They're making it for you. So the equation is 1/5 of 75 minus p. So this is the constant, and then the weight of the puppy is going to be 75 pounds when it's a dog, minus the current weight of the puppy. Okay? So we have initial condition when the puppy was first weighed, not when it was born, but when it was first weighed, it weighed 3 pounds. Okay? So find the equation. Just a baby. So we start with the equation dp dt equals 1 over 5, 75 minus p. Okay, so I can write this as 75 minus p over 5. Okay, that might help us, because how do we move our 75 minus p? If p is on top, we need all the p's on that side. So we're going to divide by 75 minus p and multiply by dt. Okay, so what that gives us is dp over 75 minus p equals 1/5 of dt. Okay, so here we have our linear equation, right? 1 over a linear equation. When we take the integral of both sides, the left side becomes a natural log antiderivative. But take notice, what is the coefficient of your variable? What's the coefficient of p? It's -1. Okay, so that means we need to have a negative outside of your natural log. Okay, 0, 3. We're plugging in 0 for t and 3 for p. Negative natural log of 75 minus 3 equals 1/5 of 0 plus c. So c is the negative natural log of 72. So we're going to put our negative natural log of 72 in here for C. So we get negative natural log of 75 minus P equals 1/5 of T minus the natural log of 72. Okay, we have a negative in front of our natural log, so we're going to divide everything by -1 to change that sign from negative to positive. Okay, it changes the negative out here. It doesn't change the equation inside. This is still 75 minus P. That's not affected by the -1 division. But this becomes a -1/5 T and a plus natural log of 72. Okay, now we're going to exponentiate both sides, raising them both from the power of E. Okay, so that cancels out, and I get 75 minus P equals, let's do this together. So now this plus is going to change into a times, right, times E to that power also. Okay? So E to the natural log of 72 brings our 72 to the front. So we no longer have that natural log of 72 anywhere. 72E to the -1/5 T. Okay, in order to solve for P, I'm going to do this kind of strangely. I'm going to add my P to this side. This becomes a positive P. And I'm going to subtract all of this stuff to that side. Okay, so I have equals P now on the right, which is fine. P can be over there. And I have a 75 minus 72E to the -1/5 T. Okay, and this is, of course, P of T as our answer. Okay, this is how calculus is going to ask you to do these differential equations, is most often they give you a story problem where the rate is a proportion to something else. And that always gives us this exponential answer. Fantastic.